Hello and welcome back. Last time we just started to look at cofunctions. So this would be the difference between, say, sine and cosine, secant and cosecant, tangent and cotangent. And the way they work is complementary angles will produce similar values, the same values. So for sine, if you plug an angle into sine and its complement into cosine, you get the same value. Likewise, if you plug an angle into cosine and its complement into sine, you get the same value. One big thing that I didn't necessarily mention last time is that so this only works for acute angles. Oops. So again, this is something that we have to make sure that the angles that we're plugging in are going to be acute angles. We don't want to plug in angles that are bigger than 90 degrees or smaller than 0. So this is something that I really want to stress because we can get some really odd things popping out. So then this last one down here, if we had tangent of theta plus 3, and I want to use my cofunction. Again, the cofunction for tangent is going to be cotangent. And the complementary angle to an angle is going to be the one where if you add it, you'll get 90 degrees. So if I want the complementary angle to this one, I'm just going to take 90 degrees and I'm going to subtract this. I'm going to take away the theta plus 3. And so then if I were to add this angle and this angle, those would cancel out and I get 90 degrees. So that's quite nice. But then if I take 90 degrees and I subtract this, what will I get? This will be cotangent. Oops, this should have been 79. I hope I didn't make that mistake in the last video. But anyway, if I take 90 degrees and I subtract this, I'm going to get 90 degrees minus theta minus 3. So that's going to be the same thing as 87 minus minus theta. Cool. So using these complementary angles, we can make some nice identities. We can turn sines into cosines or cosecants into secants if we need. Another type of question that we could do would be if we're already told that all angles are acute, so that we can use our cofunction identities, and we're told that sine of theta plus 30 is going to be the cosine of 6 theta minus 10, we know that these are going to be complementary angles. So we can find theta in here. So since this angle and this angle are complementary, when you add them together, you should get 90. So if I take theta plus 30 degrees, and I add this guy, 6 theta minus 10, I'm going to get 90 degrees. So let's start simplifying. On the left-hand side, I'll get theta and 6 theta will be 7 theta. 30 degrees and minus 10 degrees, this is going to be 20 degrees. So all that's going to equal 90. I'll subtract 20 from both sides, so I'll get 7 theta is equal to 70, and I'll divide both sides by 7, and I'll get theta is 10 degrees. So, where did I start? I had sine and cosine, and these are cofunctions. Since all the angles are acute, and I get the same thing when I plug them in, they've got to be complementary angles, meaning they have to add up to 90. Let's do one more example. Assume all angles are acute, and we'll let tangent of 2 theta plus 29 degrees be equal to the cotangent of 3 theta plus 21 degrees. Find theta. So again, we're assuming all angles are acute, and I've got cofunctions, so our angles must be complementary. So if I add up these angles, I should get 90 degrees because these are complementary angles. Again, let's simplify. So 2 theta and 3 theta, that's 5 theta. I'll add up 29 degrees and 21 degrees, so this is going to be 50 degrees. It's going to be equal to 90. I'll subtract 50 from both sides to get 5 theta is equal to 40 degrees, which means theta, if I divide both sides by 5, is 8. And that's all there really is to these cofunctions. We just have this nice identity where plugging an angle and its complement into a function and its cofunction, you get the same thing. The last very important thing for this chapter are going to be special angles, and I want to introduce where these come from and why they're useful. So, if I start with a equilateral triangle, what you'll notice is that in an equilateral triangle, all the sides will have the same length, and all the angles will be the same. So we will have 3 angles in here. If each angle is going to be theta, then what will happen here? All 3 of those angles should add up to 180 degrees, which means that each angle is going to be 60 degrees. So instead of writing theta in here, we can write 60 degrees, 60 degrees, and 60 degrees. What I'm going to do now is pretend like each of these side lengths were 2 to begin with. The reason for this will be clear in a second. And what I want to do is I want to divide this triangle in half. So we're just going to split it right down the middle. Like so. And what I can do is I can draw this red line in here, and I'm just going to draw this line straight up and down. And what this does is, if everything's been done correctly, this is going to be a right angle, and this is going to be a right angle as well. So now, after I cut this triangle apart, I have 2 right angle triangles. Down here, this is going to be 60 degrees. I haven't changed that angle. Down here, this is going to be 60 degrees. And then we can figure out that this is going to be 30 degrees up top. And there's two ways to do this. One is we're dividing this angle directly in half, and half of 30 should be 60. Also, the sum of the angles of a triangle should add up to 180. And 90 degrees, and 60 degrees, and 30 degrees adds up to 180. So I can only say that this is going to be 30 degrees. Now, the reason that I wanted to call this side length 2 was because after I cut this triangle directly in half, those 2 side lengths haven't changed. The one on the bottom has been cut exactly in half. And what's half of 2? It's 1. So having that be 1 is quite nice. So then the question is, what is the length of the cut that we made right down the middle? Well, we have a right angled triangle, so we know that a squared plus b squared is equal to c squared. As in, the sum of the squares of the 2 shorter sides should add up to be the square of the hypotenuse. So I know that, so if I call this side length in the middle x, I know that 1 squared plus x squared should be equal to 2 squared. 1 squared is 1, 2 squared is 4, so x squared is going to be equal to 3, so x should be the square root of 3. This length in the middle, is the square root of 3. And it's the same for both the triangles. They're both exactly the same. So when we have a triangle whose angles are 30, 60, and 90, the ratio of the side lengths are going to be 1 to the square root of 3 to 2. Remember that for similar triangles, all the ratios of the sides are going to be the same. So let's go through and calculate a few of these sines and cosines. So let's start with 60 degrees. So we're starting with this angle down here. The sine of 60. sine is opposite over hypotenuse. So the so part of SOHCAHTOA. OH, opposite over hypotenuse. Side opposite to the 60-degree angle is the square root of 3. And the hypotenuse here was 2. The cosine is going to be the adjacent divided by the hypotenuse. So the cosine is 1/2. And then the tangent is going to be the opposite over adjacent. So the side opposite to the 60-degree angle is the square root of 3. And the side adjacent has length 1. Now, I'm going to figure these guys out. And I'm going to do so in 2 different ways. First of all, the sine of 30, okay, we have a 30-degree angle up here, and we can just read this off. The sine of a 30-degree angle, opposite over hypotenuse, the side opposite the 30-degree angle is 1, and the hypotenuse is 2. So the sine of a 30-degree angle is exactly 1/2. And what you'll notice is these guys are the same. Why are they the same? Sine and cosine are cofunctions. 30 and 60 are complementary angles. They have to be the same value. Likewise, the sine of 60, the cosine of 30, sine and cosine, these are cofunctions. 60 and 30 add up to 90, so these are complementary functions. These guys are the same. And we can check. For our 30-degree angle, the adjacent side was length square root of 3. The hypotenuse was 2. The last thing to do is the tangent. And the tangent of 30 is going to be 1 divided by the square root of 3, which, if I rationalize the bottom, if I multiply both the top and bottom by the square root of 3, is going to be the square root of 3 divided by 3. So when we look at this, these values are quite nice, and the 30, 60, 90 triangles are also nice. The angles themselves, 30, 60, and 90, are nice round numbers, and they're easy to remember. There is one other triangle that I want to look at, and this is the right triangle, where both of the side lengths next to the right angle are the same, which means that both of the angles are also going to be the same. So again, if this angle is theta and this angle is theta, then that means that theta plus theta, as in 2 theta, plus this 90-degree angle would have to add up to 180. When I solve for theta, I get that theta has to be a 45-degree angle. So this type of triangle is called an isosceles triangle, where 2 of the side lengths are the same. It's also a right triangle. So in an isosceles right triangle, we have 2 45-degree angles and a 90-degree angle. And here, if I call this side length 1, since those are the same length, they have to be the same. So if this is 1, then this is 1. And then the question is, what is this length over here? Well, a squared plus b squared is equal to c squared. C being the length of the hypotenuse side. So we know that 1 squared plus 1 squared is, let's call this c squared. So that's just going to be 2. So 2 is equal to c squared. C is the square root of 2. So this side length is going to be the square root of 2. And we can calculate some sines, cosines, and tangents. Sine of a 45-degree angle is going to be opposite over hypotenuse. If I rationalize this, take the top and bottom times the square root of 2, I get the square root of 2 over 2. The cosine of a 45-degree angle is going to be the adjacent over the hypotenuse. And again, if I rationalize it, I get the square root of 2 over 2. And again, right away, these are the same. Sine, the cofunction to cosine, and 45 and 45-degree angles are complementary. So those guys have to be the same. The tangent, which is the opposite over the adjacent, 1 divided by 1 is 1. The tangent of 45-degree angle is a nice simple number.